All right, so here's the first of two lessons looking at products of vectors. And essentially there's two types of ways we can multiply vectors. Today, for this lesson, I want to focus on what we call a scalar product, or the dot product. That's denoted with a dot. And this represents a value that will be a scalar. There's also a vector product, which is represented with the sort of cross, the more familiar symbol that I'll talk about in a future lesson. So a scalar product of two vectors is a scalar, so your value is not a vector. And it essentially measures the or how two vectors align with one another in terms of both their directions and their magnitude. And it's relatively easy to calculate. And the vector product for another lesson is definitely more to think about. And so I'm just going to rewrite my vectors A and B here as a column matrix because I like them better. And so if I rewrite A, this is -1, 0, because there is no j value, and a 2 times b to -1, 3. And so to find the dot product or the scalar product, I just need to multiply these components separately. And so I have -1 times 2, which is -1, plus for my y values, my 0 times -1, which is 0, plus my z values or my k values, whatever units you want to think about, 2 times 6, which is 6, and altogether this equals 4. So that is what we call the scalar product of these two vectors, +4. We can use that to find the angle between these two vectors. Essentially, if I imagine these are both two three-dimensional vectors, so I imagine I have two different lines, I can use this idea to find the angle from there to there or the angle from here to here. To find that, I need to take my answer from before as well as find the magnitude of each of these vectors. So the magnitude of A is just, using the Pythagorean theorem, it's the square root of -1 squared plus 0 squared plus 2 squared, which is √5. And the magnitude of B will be just √14. And so in general, if we know the magnitude of two vectors and we know their dot product, the cosine of the angle between them is always the same as the dot product in the numerator. So in this case, just 4. Or maybe before I get to that, I'll write it out. So in this case, it's the dot product of A times B divided by the product of their magnitudes. So in this case, again, the numerator, I already figured that out, was 4, that dot product right there. And I already found the magnitudes of A and B, so it was √5 times √14. And so in this case, the cosine of the angle is 4 over √70. That means the angle itself will be the same as the inverse cos of 4 over √70. And we can think in radians or degrees. I'll think in degrees here. We get approximately 61.4 degrees. And so that angle there is this acute angle I'm showing here. Although we could subtract from 180 if we want to think about the obtuse angle. Although generally by convention we focus on the acute angle. All right. And so let's look at this. I got two lines now, two three-dimensional lines as vector equations, and I want to find the angle between them. Well, in terms of these two lines, again, I'll just kind of visualize something like this and like this. All that really matters about finding the angle between them is the direction vector. This point here and this point here represent some point on this line and some point on this line. And while that matters for visualizing the line, in terms of where they cross and the angle they form between them, that doesn't really matter. What matters is just the direction vector for each. And so if I want to find where these two angles cross, I can just ignore those position vectors and focus on the direction vectors. So in this case, that and this. And so I'm going to call the one I've highlighted in yellow, I'll call that direction vector 1. The one I've highlighted in blue, I'll call that direction vector 2. And so if I want to find the angle between them, again, I need to find a few things, one of which is the magnitude of each of these vectors. And so the magnitude of D is the square root of 2 squared plus -1 squared plus 0 squared, which is 5. And the magnitude of direction vector 2 will be root 11. I also need the dot product or the scalar product of these two. And so if I want to actually go this times this, I just need to now look at my elements in each of these. So again, like we did before, it's 2 times 1 plus -1 times 3 plus 0 times -1. So you get 2 plus -3 plus 0, which is just -1. And so again, I can use that. The cosine of my angle will be the same as the dot product, -1, divided by the product of my two magnitudes. So in this case, root 55. And here, if I use my inverse cos, I can say theta, I get approximately 97.3 degrees, which is fine. But like I said, in general, we want to focus on the acute angle. And again, whatever these two lines look like, I now know, I don't know, I'll estimate it roughly like this. There is a 97-ish degree angle right there. And in general, by convention, we tend to, let's focus on the acute one. So subtract 180 from 97.3 from 180, and I'll focus on this to 82.3 degrees. All right, so last question is essentially the same idea, but instead of being given the two lines as vector equations, they're given in Cartesian form, which, again, we don't need all the information here, but we want to first put these into vector form. And we looked at this in a previous lesson. And so remember, each of these, if we think about where these equations came from for this line 1, each of these equations that are equivalent to one another, the x plus 3 over 2 and so on, all equaled each other because they all equaled lambda. And so I want to kind of go backwards. And for example, for the x plus 3 over 2, I know that that equaled lambda. So I can say for this one here, I know that lambda equaled x plus 3 over 2. Well, that's it. Just to save myself a bit of time, I'm going to multiply both sides by 2 and write it as 2 lambda equals x plus 3. And this is for line L1. So 2 lambda equals x plus 3. Do the same thing for looking at y. I know that lambda, in this case, equals just y plus 2. And then for z over root 3, I know that root 3 times z equaled, sorry, root 3 times lambda equaled z. Well, if I do that, then I can see that if I write these in terms of just x or y or z, then I get x must have been the same as -3 plus 2 lambda. Here y must be lambda minus 2. Sorry, y equals lambda minus 2. Yeah, sorry, I thought I was wrong for a second. Actually, I'm just going to write it as minus 2 plus lambda. And I'll say y in a bit. And the other one I can just say lambda equals just z. Sorry, whoa. Sorry, it's a Friday afternoon. I probably should have just gone home, but I'm powering through it. I apologize for my mistake. In this case, it already is done. Z equals root 3 times lambda. Although I'm going to write it as 0 plus root 3 times lambda. Because if you think back from the last lesson, each of these equations for x, y, and z, the constant term, that related to my position vector, which I don't really care about, and these coefficients, the 2, the 1, and the root 3, those related to the direction vector. That's what I do care about. So for example, if I look at line L1, I can write it in vector form. The part that doesn't matter is the position vector, -3, -2, and 0. For what we're doing, it doesn't matter. Plus lambda, I'll put lambda 1 because we're looking at line 1. The direction vector I can now see was 2, 1, and root 3. That's what's going to matter here. Just this part here. All right, so doing the same thing for line L2 without going through all the steps, since it is essentially from the last question. For L2, we should get the equation in not in vertex form, in, what's it called again? My brain's dying. Vector form, that's the word I'm looking for. Vector form, the position vector, if you found it, is 1, 1, -1 times lambda 2, I'll say, and what matters is the direction vector, -2, 2, and √3. And again, that we could figure out in the same way as what I did before. And so now, essentially, all I need to focus on are these two direction vectors, find the dot product of them, find the magnitude of them, and then determine the inverse cosine of that quotient. So I can say here, I can say the cosine of theta will equal the dot product. The dot product of these is exactly 1. And again, 2 times -2 plus 1 times 2 plus √3 times √3 is exactly 1. Now, a dot product of 1 means that these two vectors are actually going the exact same direction. No, it doesn't. What am I talking about? I should edit that out. Just edit that out yourself. So, never mind. It's too far in me for me to redo this. And then in the magnitudes, I should get a magnitude of 8 and 11, or √8 and √11. And so therefore, theta equals approximately 83.9 degrees. And this is one of those times I'd say I did a pretty bad job of explaining those things because I kept saying the wrong words. I'm pretty bad at that. The takeaway from this lesson is I should not be recording videos after school on a Friday when I'm tired. I'll learn from that. I hope you forgive me.